Well, anyway, let me get started on IK, finally. Well, I'll show this later. Today we're gonna finish up IK, and then that will basically be the end of the topics that are important for modern VR. The topics that we'll cover throughout the rest of the class will be more like super emerging topics even within the field of VR, like haptics, olfactory displays, AR, and so on. So, yay, this is the last thing that is still, I guess, possible to do well, if I may. So, Friday, I build up basically all of the Friday sections because we basically lost a week and a half or 2 weeks. So the Friday sessions will be for AR mostly, and the LDoc session will be on how research in this area works and how you publish to conferences and things like that. And today we'll finish IK and I'll explain A9. So, last time we started talking about kinematics, and I got as far as introducing you to the idea of IK. And just to breeze through this part, kinematics is essentially where robotics and graphics intersect, because robotics has the goal of having these machines which have end effectors that you're trying to get to a certain position in the most optimal way, and in graphics we have animation, where we are trying to pose a skeleton in a way that looks natural, and they share a lot of actual technical content. So kinematics in general are just any method of figuring out the transform of different components inside of a structure, like our skeletal structure. And just to review some terminology, a rigid body is any non-deformable object that still has physics constraints. So any of your bones, like your forearm, your upper arm, your thigh, any of those things where you have a rigid bone that is actually controlling it. A manipulator is a really general term for any device that can manipulate things in the environment. So, it's pretty vague. Some people would consider a limb a manipulator. Some people would only consider the end effector the manipulator. I think the more general audience would consider the entire limb a manipulator, because say that you have physics on your character in the game, it would still be able to knock things over, like in Half-Life Alyx or Boneworks or any of those games. A manipulator, so the general definition is that it's a kinematic chain of components, such as our rigid bodies, that are linked by joints. And so by this definition, you would assume that a manipulator has to be a limb, but like I said, it can vary sometimes. Any joints that you can actually control, like that you can consciously control that are not controlled by some other part of your body, are actuators. So for example, you can control your shoulder directly, but and also, actuators can control some rotations but not others. If you think about your shoulder can control 3 degrees of freedom, and we'll talk about biomechanical constraints later. But your shoulder has control over 3 degrees of freedom, but your elbow only has control over 1, and its other degrees of freedom are essentially controlled by the shoulder. So, you can have actuators for different degrees of freedom, I suppose. What else? I guess. Again, this was weird to think about last time. I'm looking at my arms right now to figure this out, but your wrist, you don't directly control your knuckle orientation, but you do control the tips of your fingers, which in turn will orient your knuckles, I suppose. So your fingertip would be an actuator, but not your knuckles, if that makes sense. Physiology is hard. But anyway, manipulator, like I said, usually any structure that represents a limb. The end effector is the final device in the manipulator chain, or the leaf. So, for example, your fingertip is probably, for a really complicated human skeleton, your fingertip would be the leaf. For the simpler human skeletons that we saw, generally we'll just consider the hand itself to be the leaf. It might just be in some default pose, or it might be in a fist or something like that. But these will be the end effectors, the things that generally you're trying to get to a certain position. Because your elbow, nobody does anything with their elbow really. I mean, there are some things you can do with your elbow, but generally your hands are doing all the work, or your feet are doing all the work. So they are the things that you're trying to get to a certain position. Where your elbow is while your hand is in a certain position is not as important as long as your hand is where you want it to be. So forward kinematics is something that you're already more or less familiar with. If you have the transforms of all the parent joints, where is the object at the end? And we saw an example, which I'll show you in a bit, where you want to know what the world position of a game object or an actor is. In order to get that, you can just merge the local transforms of all of its parents. So in the second lecture of the class, the graphics lecture, we looked at this example. If you have these planes and you have this parenting structure, you can very easily figure out where the red cylinder is, which is in this case the end effector, by adding the local orientations of each of the parents. So in this case, the blue plane's local height is 0.1 meters, the white plane's local height is 4 meters, and the red cylinder's local height is 1 meter. Therefore, the red cylinder's global height is 5.1 meters. You just add them all up with scales, you multiply them, and you just go up to the root, and that will give you all the information you need. So this is more or less how forward kinematics works, although this is the very game engine-y example. And Unreal and Unity both have the structure where the game level's name is the root of the world. So where is 000 considered in the world? And then everything else, it's like the super parents of everything in the scene. And so forward kinematics is pretty simple, but it has a lot of limitations. For example, you need to know pretty much all of the parent joint transforms, which we can't easily get in VR. Because in VR, as you might have noticed, you can really only track the headset and the controllers. We have to make really strong estimates about where anything else is. Another thing is camera setup. Most of these headsets that do inside-out tracking nowadays have cameras only on the front or in the sides. And in some cases you might have peripherals, like the Vives have Vive trackers, which are these little triangular devices that can track arbitrary objects in the scene. But in any case, for wireless headsets, you can't really use that yet. But anyway, if you could potentially have external cameras that track like your body, for example, the Xbox Kinect. But again, these are external cameras, and even if you were to embed hundreds of cameras in the headset, you have problems like cameras are pretty expensive, especially if you're trying to build them into an ergonomic headset. And yet ergonomics, well, here financially speaking, they're expensive. They're ergonomically just ugly, and they eventually will make the headset really bulky because you need to fit those wires somewhere, and so on. You need to place them specifically. You need to do the extrinsic calibration, those of you in computer vision. Cameras are expensive in terms of hardware. There's a lot of CPU load. There's a lot of CPU overhead that goes into rendering an image, or grabbing all the bits from the camera and spitting them out onto an actual image. So that'll be slow, and these are mobile devices nowadays, so they're even slower. And even if you were to add an infinite number of cameras to your headset, you would still suffer from occlusion, because it's still possible for some joints like the elbow to get blocked. And so in general, with these modern devices, we want to be as egocentric as possible. And like I just said, even if you are totally egocentric, like the Oculus Quest, and you add some infinite number of cameras to the headset, you still have problems like occlusion. So this is where IK will come in, because you can predict the rest of the kinematic chain. So I changed the example of our planes to work better with the IK explanation. So we still have this parenting structure where the blue plane is the parent, or the grandparents, the white plane is the parent, and the cylinder is the end effector. Except in this case, we know where the red cylinder is globally, and we know how far the white and blue planes can be from it. And so from there, we can go backwards and say, okay, so white can only be 1 meter below red, therefore white must be 4.1 meters globally. Blue can be 4 meters below white, therefore blue can be at 0.1 meters. and then you can go back and figure out the local transforms given this parenting structure. That's essentially what IK is. You're just going in reverse, or the inverse, or whatever. And whether you want the global or local transforms, that's, it depends heavily on what you're trying to do, what API you're trying to work with, and so on. Like some of the things that you did in A7, for example, made the assumption that you're working in local space, which isn't always the case. Like, for example, with skeletons, you want to work in local space because your animated character can be facing any direction in the game. So for a slightly more complex example that makes you think about rotation, you have this parenting structure, which is still pretty similar. The blue is the grandparent, white is the parent, and red is the end effector. And here what I'll tell you is blue is at this location. It's at 0, 0, and red is at some other location. You know how long the white cylinder is, and you know how long the blue cylinder is, and you know that the white joint cannot bend upwards, so it can't be angled like this. From there, if we were thinking about this in a skeletal animation context, I might ask you, what rotations do I want between these things such that I can, I don't know, make some character like from Mixamo, make their arm follow this kinematic chain. In that case, you need to know the angles, and we'll see how we do that soon. But yeah, this is essentially the human arm kinematic chain. You have a shoulder, an elbow, and a hand. And you might not know immediately how to do this. We'll actually see some math later that you probably haven't seen since high school, but it's actually not as complicated as you would expect. It's just a different thought process. And IK only gets more and more complex. Like what these papers from like Google were working on, this Google DeepMind paper, what they were trying to do was have these virtual agents which only know the joints. They don't know any of the constraints. They tried to have these creatures learn the constraints basically, and learn how should we rotate each part of my body around the joint such that I can move at as fast as possible and avoid obstacles and so on. So I'll speed this up a little bit, but this is a cool paper. I think a lot of people have seen this, but it's a cool paper to read anyway, and they had a couple of examples. They had a human example, they had this spider thing example, they had that one stick figure example. And even though this thing has 4 legs, it's still easier than the human kinematic chain. The human kinematic chain is actually pretty complicated. So that's why we actually put effort into thinking about it, because this is our goal, to get a human that looks natural. Obviously this one doesn't, but it's still working within the constraints of its joints relative to the rigid bodies that the joints are attaching.
That would work for a horror game, though. I would be terrified to see that. Yeah. Imagine
yeah,
if that came running towards you.
that would be pretty cool. The spider as well. Or I don't know if in Resident Evil 7 they had creatures like that, didn't they? They had like the woman, I think, turns into a giant monster with a bunch of arms hanging out of it.
I didn't play that one, but it was pretty terrifying.
Anyway, so IK addresses this problem of limited knowledge. We know where the end effector is, but we don't necessarily know where anything else is, so we're trying to predict it, given what we know about the system itself, such as rigid body lengths. We use IK to solve a lot of problems. In a lot of ways, robotics is IK fundamentally. Almost a huge percentage of the problems in robotics try to solve IK-related problems. And in graphics, a lot of stuff is dependent on IK. You can sort of think of IK as some system of equations where the variables are each component of the transform of each joint. So as you can imagine, if you have too many joints, this system of equations gets really, really complicated and hard to solve. And your IK solution, like the solution that describes all the joint orientations, you might have 0, 1, some specific range, or even infinite solutions, depending on how much information you're given about the IK chain or the kinematic chain. And we can adjust these this range using constraints. And so we try to seek this balance between having too many constraints or not enough, which we'll see in a second. So how do you actually solve IK problems? Just the same way that in machine learning you solve these max likelihood estimation problems where you're trying to you're trying to find the weights of your network that give you the best prediction of the data. There are a few ways of solving IK problems. Generally speaking, you have analytical solutions or iterative solutions. So analytically, what we can do is just derive the solution from all the equations that we know are true for the system. So an example that you've probably seen, a lot of you are in 562 or have taken it. So the analytical solution for MLE problems would be compute the derivatives or the Jacobian and then set to 0, because that will be, when the gradient is 0, that means that you're at the local minimum and you don't need to. If your local minimum is the minimum on some n-dimensional space where n is the number of parameters, if the gradient is 0, that means that you've reached an optimal solution. I mean, it's a hand-wavy way of explaining it, but I think most people know what gradient descent is. Otherwise, I'll explain it in a little bit. It'll show up again. The iterative solution might be you define error, so what does it mean for your guess to be bad, and you improve on it. So, for example, with animation, delta rotation might be too high, like your character's arms are in too extreme angles. Or maybe your iterative solution breaks constraints, such as maybe it assumes that your arm is longer than it actually is. So after you define what the error means, you can make a guess, you calculate the error based on this guess, then you use information about how much error there is to make another guess that will result in less error with gradient descent. And you just keep doing this over and over again until you're happy. These are iterative solutions. And you can mix and match iterative and analytical solutions. So those of you who have a decent amount of machine learning experience will know that some parameters you can just figure out mathematically without having to iterate. In other cases, you might have variables that are free or bound. So a free variable, for example, is one that is completely unknown and you can choose any value for it. So if any of you remember parametric equations where you have an x equation and a y equation, and both of them are dependent on t, which is some variable that you choose, t in that case is a free variable. You can choose any value for it, and the assumption there is that x and y will give you a reasonable answer, although that's obviously not always the case if your parametric equations are not contiguous or something. A bound variable is similar, except you do have a range of possible choices, and thus a range of possible solutions, usually, including maybe 0. In graphics, the analytical solution is often geometric because we have visual solutions to most things. Like an analytical solution usually has some geometric definition. So with the redirected walking assignment, for example, there was a reason that we were doing delta yaw relative to center. We wanted the user to turn towards the center. And physically, we know that towards the center means if the center is to my right, then I want to turn right. If the center is to my left, I want to turn left. So there's some graphical context for these analytical solutions. And also, because we're limited to 3D space for most of our computations, or if you're doing transform computations, you have a 6-dimensional space, you have 3 rotational parameters and 3 translational parameters. Even 6 parameters is way fewer than you're likely to find in machine learning. So in graphics, we tend to have more robust and actually feasible analytical solutions. They're just easier to derive in general. And yeah, like I said, there's usually some graphical definition. And we also have relatively intuitive constraints. So, one of the reasons we use Euler angles is because Euler angles make sense to us. Like, we can imagine on a unit circle what it means for something to be rotated a certain way. Like if my arm is rotated, like if my elbow rotates by 30 degrees, you know what that means graphically. So the long-time preferred iterative method, which was used for at least 20 years, I think, at least 20 years before 2011 when a new method came out that we'll see. This was the preferred method called CCD. It's cyclic. I always mess up the pronunciation, or it's ambiguous, but I'll say cyclic coordinate descent. And this is similar to gradient descent, except what you do is you update each axis instead of trying to update everything at the same time. But it is still, it's a similar idea to gradient descent. So this is gradient descent, for example, or coordinate descent, depending on how they actually did it. But the idea, you can think of it as rolling a ball down a hill, and the bottom of the hill is or the valley is the optimal solution. But anyway, what they basically do is, for each joint in the kinematic chain, they basically just rotate each joint just a little bit until the end effector is as close as you can get to whatever your target position is. So you can think of it as, if you're in pitch black and you're trying to reach for a wall, you kind of just stick your hand out and then rotate it around a little bit. Or you just start rotating it randomly to try to find the wall. That's sort of what CCD does. But again, this is an older method, so I won't go into it. And I think that most people have some idea of what gradient descent is. So again, I don't think it's worth explaining mathematically why this works, because you either know it or you will never have to implement it, because nobody really does this from scratch anymore. There's a problem with this method. It doesn't really consider constraints. You can modify it to consider constraints, but what it definitely can't handle right now is continuity. So CCD has this problem where you have sudden jumps, or you have these weird poses. So for example, this guy, Boney M guy dancing, he has strange poses that CCD could possibly create for him. Also, CCD, its solutions by default are unconstrained, and a large range of these solutions is actually impossible anyway, for a human especially. And another thing is that we can't move that. We have constraints on how much we can move, which, if we're thinking about it in a robotics context, robot arms are not as constrained as our arms are. And also, in VR especially, we have to think about biomechanical constraints. So, we have a human inside of the headset, and they have body constraints, and joint constraints, and speed constraints, and so on. So, anyway, a better solution to CCD came out in 2011 that's very popular in game engines, called the Fabric algorithm. This is forward and backward reaching inverse kinematics. And it's similar to CCD, but it makes some stronger assumptions. It's similar to the EM algorithm, or no, EM algorithm is not the same. I don't remember the name of the algorithm in machine learning. It's not important. Anyway, what Fabric does is essentially treats your rigid bodies like a bunch of line segments, and it tries to find the positions of the points, and then from there it tries to figure out the rotations, instead of CCD style where you just rotate it a little bit until you get to a rotation that works. So right now you're more or less familiar with how skeletal animation works. If you think about what limitations we have, because we're thinking about the rigid bodies as line segments, we need to know the bone rotations. Otherwise, if you try to translate bones, it'll cause really strange problems that we've already seen. Otherwise, I'd be glad to show you examples. I have tons of them. So one way or another, we will have to calculate the rotations. But I'll show you a more detailed version of this, but what Fabric basically does is it first makes some reasonable prediction about what your parent joint positions are based on the end effector position. So you might choose some initial value. In a lot of cases, if you think of it as Fabric can run every frame, and for each frame what you can do is use the previous frame's orientation as the prediction for the current frame. Anyway, that's what the backward step is. So you're going backwards from the end effector and figuring out all the parent joint positions. Well, you're actually predicting the delta orientations. So even if you have the previous frame's data, if your end effector moved a little bit, like if your VR controller moved, your parent joints would have moved some small amount as well. But anyway, after you do the backward step, where you make some prediction about where these joint positions are, what you do is you start from the parent and then go towards the end effector, and you correct the predictions based on the constraints. We'll see in a second. I have a better explanation in a bit. And like I said, you can just use the previous frame as an initial guess. And what this will do is make sure that the motion is continuous because you're using the previous frame. So unlike CCD, you're not choosing an entirely new working orientation every frame. Here we are actually using the previous frame. Before I explain in more detail how it works,
is defined as the
here's what Fabric is trying to do. So they're moving the end effector around, and this thing is, this kinematic chain is trying to follow it. Here they show some examples compared to other methods. So CCD, you see, it finds a solution that works very, very quickly, but the orientation obviously isn't going to work for like a human. And these other methods I think are Jacobian based, so they used analytical solutions, but analytical solutions are very slow. And remember that, I don't know if you remember from the graphics lecture, but like I just said, in graphics, the analytical solution is usually the geometric one. And if you recall the graphics lecture, we try to avoid geometric solutions if possible because they're pretty slow. I think the very last slide of that lecture said this. Anyway, this is a video that you can check out if you're interested in the comparisons. What they find basically is that Fabric runs very quickly. It doesn't require many iterations before it figures out an ideal pose. And in terms of the amount of time it takes, it runs quickly enough that you could run it every single frame, which is why game engines use it. And Fabric has constraints you can add. So, for example, if this joint here can't make such a sharp angle, you can just constrain it. And CCD you can also constrain, but even so, it's not great at finding good poses. And you can also sort of see the behavior I mentioned, where it's just kind of like reaching for the target. Fabric's a little bit smarter about it. It's not as naive, I suppose. CCD I think is very close to what you would find in like a greedy algorithm. And they show some more comparisons that show like the smoothness of Fabric as compared to other methods. You can see it does a pretty good job. The technical details of Fabric aren't super important for us, it's just good to know that this exists. You might impress people in the game dev community. And Fabric also works for multiple joints. So, for example, if you have a hand, you can get the fingers to move to this position, which is actually how devices like the Valve Index work, for example. I believe they just sense the fingertip position and then they figure out everything else with Fabric. But anyway, to describe the Fabric process roughly, the first thing you do is you make sure that your end effector can actually reach the target position given the rigid body length. So, for example, if your target position, let's say that you put your VR controller on your desk and then you walk away from your desk. The first thing that you would check is to make sure that the character mesh can actually reach that far. Like you don't extend their limb. Like you don't stretch their limb to get to that position. What you do instead is you just extend it as much as you can. So for example, your wrist can't be farther from your shoulder than the length of your upper arm plus your forearm length. And your ankle can't be much farther from your hip than thigh plus shin. In the backward step, what you do first is you figure out the direction from your current end effector, or in the very first step you figure out the vector from your current joint, which will initially be the end effector to the parent joint. You normalize it because the distance from the current end effector to the old parent might be longer than your rigid bodies will allow for. You multiply it by how long that direction actually can be, and then you just find the location of the parent that way. You just add it to the current joint location like the end effector, and that will essentially go backwards. So if my end effector is here and my old joint position is here, or let me open my pointer. If I have, let's say that I have an arm that's like this, it's just like an L shape, and this here would be my end effector, and I move it this way, what I would do is from this position I would shoot a ray to the old parent joint. I would normalize it, and then I would figure out how long, how far away would the parent joint be now that I've actually moved. Like in this case, if I have an L shape like this, and I move my arm, let's say closer, so from here, and then I move the end effector here. The end effector is now much closer to the parent, and so the parent needs to go that way more. But anyway, I have a video example that you can watch if you're interested that gives a better explanation than I would. Anyway, you just keep using you use the new parent location to go through this process again until you get to the root. Unless you're really lucky or your arm didn't move at all, if you go backwards, you're basically just predicting where the root is, but it might not be accurate. So in the forward step, what you do is you start from the real root towards the end effector. You do this process going towards the end effector, and you essentially correct it. I'll show you the video, which it explains it better. But again, this is basically the same process. You figure out the direction to the next joint. You make that vector a length that is essentially how long that rigid body can be, like from your shoulder to your elbow, for example, can only be a certain length. And then you add it to the shoulder, for example, and that will give you the predicted elbow location in the forward step. And then you keep doing this until you reach the end effector. And you keep doing this over and over until they converge. So I left some pseudocode here for if you ever want to implement it yourself. Oh god, I held it too fast. Anyway, this guy I think gave a pretty good explanation, so if you're interested in how this works, you can check out his video. But what he's doing, this is a good visual explanation. So you're trying to move to this goal position. So in the backward step, what you do is you draw rays that are of length of that joint backwards. And the problem with this is that, like I said, it's just predicting where the root is. And your prediction of the root might not be aligned with where the root actually is. So what you want to do is the forward step, which will correct that. And then you keep doing this over and over until your predicted root and your actual root positions are within some threshold. So in the forward step, you start from the root, and then you do the same process backwards. And this will give you a prediction of where the end effector is. And then from the new predicted end effector, you would go backwards again, and you would keep doing this until it looks right, I guess. Until all of the constraints actually are met. The length constraints in this case. But again, knowing exactly how this works I don't think is important. This guy had also this visualization he made in Roblox. That just shows you how it works. I don't know why he made it in Roblox of all things. But I mean, you can see it works. And you also have multiple joints. So yeah, for each joint, if you were doing a branch of limbs like this, what you could do is essentially treat the intersection point like the root of this local space and iterate that way. But anyway, I would argue the technical details are not that important, but I think it's a pretty cool method, and it was groundbreaking for game engines. In VR, so obviously the nice thing about this algorithm is that it's fast, as we saw, and it's commonly used and supported by game engines, which is always nice, and it's pretty robust compared to like CCD. As we saw, it doesn't generate such extreme rotations. The problem is that there is still other constraints that Fabric, or at least in the state of the art of game development, people don't think about as much when they're working with Fabric or any kind of IK method. So yes, Fabric does preserve things like continuity, but by default what it doesn't worry about is something like can this limb actually rotate this much, or can it be this flat or something like that. I have better examples later with actual humans. So a recent trend is to use biomechanical constraints to fix this problem. And as we saw when we were talking about skeletal meshes, you do need to eventually calculate bone rotations, which is a fun thing on its own, because rotations have a lot of annoying problems associated with them. For example, just like with steer to sensor, you still have this problem where the rotation can jump from 0 to 360, or it can jump from 0 to negative 360, which is an equally annoying problem, or negative like 359.99999. I mean, rounding errors and so on. So you might want to do the decalculation anyway that we did in steer to center, just to figure out the delta transform as opposed to like world transform. There are also jumps that you get. For those of you who are more geometrically inclined, you'll know that when you do vector subtraction in one quadrant versus another, the value might change. Like some things like cross product can switch signs and things like that. We might see an example, but usually when this happens, you can tell when it's happening because another rotation will flip. For example, let me think. I think when pitch passes this threshold, or when it has like a sudden jump like this, at least in Unreal, yaw will go from like 0 to negative 180 all of a sudden, or 0 to positive 180. So you can use those sudden changes. You can use a sudden change of another axis to figure out if this one is continuous, and you can adjust based on that and force it to be a continuous rotation. Anyway, these are fun things to talk about. 3D rotations are also harder because if you're not careful, you can cause cyclic dependencies, because there are a lot of rotations in a human bone structure if you're not constraining anything. But biomechanical constraints will make this easier. And you can read the original fabric paper if you're interested, but in the original fabric paper, they actually do explain how you would get rotational constraints at a high level. And the way that they do it is, they did explain a very high level, and it's not particularly easy to implement. But fortunately, in VR and with human motion, we have these extra constraints that will make it possible to solve things analytically. So for VR and AR purposes, what we typically would use fabric for more is like motion smoothness. But anyway, it'll make more sense after I explain a little bit more. Here's the original paper if you want to check it out. And like I mentioned before, the valve index detects fingers basically by doing fabric. The valve index controller, I think, only measures whether or not your fingertips are close enough to each part of the controller, not if any other part of your hand is there. But your fingertips are a good enough, that is sufficient information to figure out the rest of your hand pose. So, moving on. Biomechanical constraints are these constraints that, they're biomechanical, as in your body literally cannot rotate that way. So, if you think of the way that you can figure out these constraints yourself is, think of your skeleton as if it's a tree, like in skeletal animation as we saw. Try holding the parent bone. For example, if you're trying to figure out your wrist rotational constraints, hold your forearm still and rotate your wrist around, for example, and try to figure out how much your wrist can rotate in each direction. And this is how you can figure out the biomechanical constraints of each child joint. And obviously some people are more flexible than others, so it's more of a calibration, if anything. But the assumption that we make here is that bones can only rotate, which is the case for almost all the bones in our body, except for the foot bones, as we'll see. But making this assumption that bones can only rotate it does simplify calculations a lot, because you remove 3 degrees of freedom, basically. You remove the translational degrees of freedom. And it's, in general, just a good enough approximation. So basically the same reasons that we only try to use rotation for skeletal animation. So these foot bones, they do technically translate, but if you think about it, how often do you actually see a virtual character's feet? Not really often. In fact, I don't even think that most characters model toes. Also, the more that we can limit the degrees of freedom, the better analytical methods we can create, and these will motivate our constraints. So, as a quick example of how useful this is to know, how many degrees of freedom do each of these joints have? I'm going to rush a little bit because I only have so much time. The pivot joint here only has 1 degree of freedom. It can only rotate like this. The ball and socket joint, like on your shoulders or your hips, it has 3 degrees of freedom, as you can see. Also, you can just count the number of arrows in this image. It's a pretty good picture. A hinge joint, like in your elbow, also only has 1 degree of freedom. You can only rotate your elbow up and down. Like I mentioned way earlier, most of the other most of the other motion is done by your shoulder, not your elbow. Think about what you can consciously control. A saddle joint, like in your hands, has 2 degrees of freedom. This joint here, which is also in your, it's also in your wrist somewhere. These have 2 degrees of freedom. A planar joint, like in your feet, has 2 degrees of freedom as well. So as you can see, you don't have 3 degrees of rotation for everything. And as a quick example of the arm, we'll see how much this actually reduces the complexity of the system. So if we have no constraints, and you think about your arm kinematic chain, the shoulder would have 6 degrees of freedom, your elbow would have 6 degrees of freedom, and your wrist would have 6 degrees of freedom. So this is 18 degrees, or 18 variables you can think of, to solve for when you're doing this. At this point we're pretty much approaching machine learning like solving, which is, slow and not usually real time at all. If we constrain ourselves to only rotations and not worry about biomechanical constraints, for each of those joints we have 3 degrees of rotation, or 3 degrees of freedom, which, that reduces our number of variables by half, which is already a pretty notable improvement. Then if we add the biomechanical constraints, given how many degrees of freedom each joint can move, the shoulder has 3 because it's a ball and socket joint, the elbow has 1, and the wrist has 2. So now we only have 6 degrees of freedom. So we have a third of the variables to solve for, as compared to the original naive method, which is pretty important. This means that we have to calculate fewer constraints. So for the elbow, there is no point in calculating or even putting in our code constraints for the other 2 degrees of freedom that our elbow can't rotate, because we literally don't have to worry about that. Our elbow can only rotate one way. Also, in terms of the amount of algorithmic complexity, this will become technically more feasible, and the extra benefit is that because we're using biomechanical constraints, how our bodies actually move, these motions will also be more natural. So if you think of it this way, algorithmically, I hate the Google Slides thing. Your complexity for like fabric, for example, would be basically the number of iterations that it takes to converge. So for that chain that we saw in the video, there were like 9 joints and it required 15 iterations, times the number of joints that you have squared, because you have forward steps and backward steps, which both iterate through all the joints. So another thing to think about is that the number of iterations to converge will probably skyrocket with the number of joints, so there's some dependency there. So having more joints just accelerates the amount of technical complexity that it takes for the computer to calculate an ideal pose. So knowing the biomechanical constraints helps a lot. So in this example of arm IK, in VR, it's a pretty simple task, and it's becoming more and more common to figure out the elbow location. And remember that in VR we typically only track the headset and the controllers, but we might still want the user to have a mesh so that they can see themselves in mirrors, they can interact with other people, they can customize their avatars, and so on. And based on previous lectures, we know what the benefits of being able to customize your avatar are. And so we don't have enough time to make this interactive, but if you think about ideas of how we can start with this, with the assumption that we can just do this in 2D for now, like looking from the side of the character, what we can do is first just choose a target mesh. A few lectures ago I gave you examples of where you can get free meshes, like Mixamo. With that mesh you can calculate their rigid body length, so how long can their arm actually be. So for example, if you're thinking about the arm system, you need to calibrate for the upper arm length and the forearm length. You can also calculate these automatically, because in Unreal and Unity you can get those, each joint as a game object essentially. And you might need to know the height of their neck and their shoulder width to predict the actual shoulder position. Otherwise you can kind of just naively hard-code it, but that's not a great idea. Then you might want to figure out the biomechanical constraints of the skeletal mesh itself. And I'll show you some more images that make this clearer, but you might also want to make some assumptions, like for example the shoulder will rotate with head rotation. Or another thing you could do is try to orient the shoulder based on where the controllers are. But again, these would just be very rough assumptions. And you know, you might have seen in games like Boneworks that, you know, it's a good enough assumption. I mean, how often do you really see your shoulders in real life if you're not in front of a mirror? So I chose this mesh, for example, in one of my examples. The biomechanical constraints for this mesh might be, and also these are judged from the x-axis, the local x-axis of each bone. So for example, the wrist rotation would be based on the local x-axis of the forearm bone. But anyway, let's say that the shoulder can move from like negative 115 degrees up to positive 75 degrees. The elbow can move from like 0 degrees here to 150 degrees or so here, which means that the elbow can only bend upwards, which you know, because if you play with your elbow, you'll notice that you can't actually move it downwards. And your wrist itself can move like maybe negative to positive 45 degrees. So from here, you can apply constraints on how much this mesh will actually be able to move given where your controllers are. And so if we want to solve for the actual positions and figure out the elbow transform in particular, what we can first do is figure out or make some estimate of the shoulder position. For example, we can just add the neck height plus the shoulder width, or half of the shoulder width if you recorded it. If you recorded, like, it depends on whether you recorded it from the neck to the shoulder or the entire shoulder width. I don't know, it's not important, these minor details. For now, if we just figure out the position, then what you can do is assume that your rotation of your controller is actually your wrist rotation, which is basically always going to be the case because you can't really move your controller with just your fingers. Then to figure out the angles between these parts of the system, you can use the law of cosines, which you probably have never seen since high school trigonometry. But the law of cosines is how you figure out the angles and sides of the triangle given at least 3 pieces of data from the triangle. In our case, we have a side-side-side triangle, because we know the forearm length, we know the upper arm length, and we can easily figure out how far the shoulder is from the wrist. And so this will complete the triangle distances. And so what we are actually solving for are all the angles. Then once you figure out the rotations or the angles, and you merge the angles into rotation somehow, you can apply them to the mesh bones. With different meshes might have different rotations. So for example, what it means for this character to rotate their shoulder such that their palm is up might be defined differently than some other mesh that's not from Mixamo. Another thing is that we have sudden rotational flips, like I mentioned before, like with the steer to center. I mentioned, I guess you'll figure this out during A9, so I won't go into details, but you can use angle flips to figure out when there are problems with the rotations. Otherwise, you can use biomechanical constraints to figure this out. Like for example, if your elbow would suddenly bend the other way if you were to move some distance, you know that you should probably add some 90-degree factor to your calculation or something. In VR, we can make a really cool assumption that you usually can't make anywhere else, which is that a user who is playing your game can't actually move the controller more than what their own body would allow. We actually have, in IK, we have the opposite problem of steer to center. In locomotion, we have the problem in VR that the user can walk anywhere they want. We can't just put a capsule collider around them and stop them from moving somewhere like we can with a normal game. So that makes locomotion a bit harder. But in IK, we have the benefit of they can't move past their own bodies, so we don't actually need to constrain their own motion. We just need to figure out how the mesh will be oriented based on that. Again, this assumes they're actually holding the controller. And in 2D, the biomechanical constraints are mostly used to limit this angle, but we don't really need it to predict because it's so simple to do law of cosines in 2D. In 3D, we do need to do prediction. So I won't go into detail because in A9 you wouldn't do this, and nobody really does this manually. But in 3D, you need to get biomechanical constraints for all of the degrees of freedom for each joint. And a lot of the times what people do is project the triangle basically to each local axis, and they do law of cosines in 2D, and then they merge the results together. They essentially solve for each axis individually with coordinate descent or fabric or something like that. And a lot of the times we do need to predict at least one of the joints. So for example, I might be able to figure out the elbow location relative to one 2D plane, but look at this example where the hand is oriented the same way, but the elbow can actually have a difference in rotation here. And so I might just need to predict this and try to make it as continuous as I can. But what you'll find is that your arm length actually does help restrict this rotational range. And you can test this by just keeping your hand in one place and trying to move your elbow. You'll find that it's actually not as high of a range as would be problematic. And a lot of the times the hardest part is just converting between different angles. If you remember switching from Euclidean to polar coordinates and how much of a pain that is, we are basically doing that, or at least we're doing something equally as annoying as that in 3D IK. And fortunately, game engines already have IK solvers, so we really don't need to do much calculation manually. In the 3D modeling program where the mesh was created, you can create IK yourself, or you can do them programmatically. Unity and Unreal both have plugins for this. And these game engines all have some function that is like, if I were to move the end effector, like the hand for the skeleton, just automatically pose everything in the ideal way. And you don't have to do any more effort than that, which is nice. And there are a lot of great tutorials online, and I probably can't explain this better than they can. Okay, we're at the end. Sorry for taking long, but just to explain what A9 will be. In A9, which I'll write up very soon, you'll have a Mixamo character, and what you want them to do is you want their arm to follow some 2D VR controller. And I'll just give you a template, one for Unity and one for Unreal people, and you will position the wrist and the elbow, and you will also make the skeletal mesh follow these joints. And I'll make sure to limit the controller motion to be actually possible. Like for example, it's really hard to get the controller behind your back. And you're free to use the built-in IK methods, but the problem is that game engine IK methods don't automatically handle the constraints, and most free meshes that you'll find online, like Mixamos, don't already have IK in like the CAD definition. And another thing is that game engine IK methods are black boxes essentially, so you might not know how they're doing this stuff or how to correct it. And so for this assignment, I'll give you a lot of resources as well to work with, and obviously I can help if you're having trouble, but you can do this in one of two ways, and either one will work depending on what you feel comfortable doing. You could just add the IK in the 3D modeling program, which will force the game engine to actually abide by the FBX file. If you are comfortable with Blender or Maya, this might be fine. Otherwise, if you didn't like the Blender assignment very much, you're definitely not going to like this. Otherwise, you can use the geometric solution. You can use law of cosines and some angle checking and some constraints and do it yourself, which is how I did it. And it actually didn't take me too long, but it didn't take me too long, and I haven't done it before, if that makes you feel better. This is the first time doing it manually, and it wasn't too bad. There were just a lot of annoying little checks, like angle flipping. Assignment 9, I mentioned this in the very beginning of the class, but the IK assignment will be comparably difficult to A7, but I think the reasons will be different and it'll be a little bit more fun. And fortunately, A7 got you familiar with actually getting these vectors. And if it makes you feel better, IK is a really, really marketable skill right now in AR, VR, and robotics. So if you ever plan on continuing in this field, it'll just be useful. Let me just show you quickly the example that I made. I have this Mixamo character, and I have this red ball with a cone that describes where the hand should point, and my character just follows it. But I didn't constrain everything, so obviously this isn't going to work. I did constrain the shoulder, and I constrained the wrist to some extent, but I didn't do it that well. As usual, this assignment will be graded based on if it's relatively good, if it's good enough, as opposed to being perfect, because it's hard to do it perfect, especially if you're doing it manually. What you don't want to happen essentially is this, for example, these sudden jumps, these horrible breakages of the mesh. Those are the main things you want to avoid for this assignment. But apart from that, I think there are a lot of resources that will help you do this. unlike the locomotion assignment. So, you know, it'll be hard, but like I said, for different reasons. And I think it'll be even more useful than locomotion. So anyway, sorry for taking longer. Bye. You can leave.